Hello, Math 7. We need to take a brief pause on solving differential equations and go back to linear algebra and talk about some stuff from linear algebra before we move on to further chapters, because we're going to need this just like we needed those things from chapter 4. So without further ado, here we go. So we're only going to do one section from this chapter right now, and this is about eigenvalues. And so let's just talk about what the definition of an eigenvalue is, okay? So if A is an n by n matrix, then a non-zero vector x in Rn is called an eigenvector of A if Ax is a scalar multiple of x. That is, if Ax equals lambda x for some scalar lambda. The scalar lambda is called an eigenvalue of A, and x is said to be the eigenvector corresponding to lambda. So eigenvector. So we have eigenvectors and eigenvalues. And before we dive into what exactly this, how exactly to define them, let's just kind of just take a look at what this looks like, okay? So let's take this matrix A equals 5, 2, 0, negative 1. And I'm just going to tell you that 5 is an eigenvalue, and the vector 3, 0 is a corresponding eigenvector to 5. And so what I want to do is let's compute A times V and 5 times V, and let's see if we get the same thing, okay? So A times the vector 3, 0 is 5, 2, 0, negative 1, oops, times the vector 3, 0. I'm usually pointing to things on this, so I need 5 times 3 plus 2 times 0. So that's 15. And then I get 0 times 3, negative 1 times 0. That's an easy one. I get 0. So there's A times 3, 0. Now let's compute 5 times 3, 0. And that one's faster. That's just 15, 0. And as you can see, we get A times 3, 0 is equal to 5 times 3, 0. And so multiplying the vector by a matrix gives us the exact same thing as multiplying the vector by a scalar, okay? So how do we find the eigenvectors and the eigenvalues? And the computation isn't so bad, but I actually want to kind of show you where it comes from here. Okay. So I have AX is equal to lambda x. Well, let's subtract, and I get 0 is equal to lambda x minus ax. Well, let's factor out the x. And I can do that. Lambda is a scalar, so I can only factor out this x thing if I put a matrix in its place. So lambda I minus a x. Now, what will happen is lambda I minus ax it is equal to the 0 vector here in this case, all right? Now, x is going to be the corresponding eigenvector. Of course, the 0 vector makes this happen, but that's not very interesting. Of course, a times 0 is lambda times 0. That's not what we're thinking about. So for a non-zero x, this system here, lambda I minus a, if this thing rho reduces to the identity, then it will essentially say that x is 0, right? Because that's how that thing will reduce. So this lambda I minus a thing, I want to find out when it rho reduces to not the identity vector, okay? So I want to know when this thing is not invertible, which is another way of saying I want to know when this thing has determinant 0. Okay, and that's where this thing comes from here. So if A is an n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation determinant of lambda I minus A equals 0. This thing is called, we've seen this one before, the characteristic equation. This is called the characteristic equation. Okay, now there are tons and tons of uses for eigenvectors in math and the sciences, so we're not going to go too far into that, but we're going to need them for our own class. Let's start with a 2 by 2 matrix here, and let's find the eigenvalues of this thing right here. Oh, before I do that, some books do A minus lambda I. I do lambda I minus A. This is how I learned. This was the way I stuck with it. Some books go the other way around. It's totally fine to do A minus lambda I. It will give you the exact same lambdas. I'll show you why I like doing it this way right here. Okay, so these aren't so bad. You just do a determinant. In fact, if you recall, I did some determinants like this with variables back in chapter 3. So just compute lambda I minus A. And I'll do this kind of the long way once, and then we'll just kind of do it in our head from now on. So this looks like determinant of lambda I is 0, 0, lambda, just like that. Minus A is 5, 2, 0, negative 1. And so I need to do all that and then take the determinant. I'm just going to work across here. Now, as you can see, on the diagonal, it's going to be lambda minus that entry, and then lambda minus the entry. And then off the main diagonal, it's just make it negative. So negative 0 is 0, and negative 2 is negative 2. So off the diagonal, that's what I get. So what is the determinant of this thing? Well, it's lambda minus 5 times lambda plus 1 minus 0 times negative 2, which is just 0. Okay, now I want to know, when is that equal to 0? When is lambda minus 5 and lambda plus 1? When's that equal to 0? Well, lambda equals 5 and lambda equals negative 1. Those are my two eigenvalues of this matrix right here. Okay. Why don't we try it for something a little bit bigger? So as we can see, what's going to happen, I forgot something. So why I like doing lambda I minus A is for this reason. So you can see when you take the determinant of this thing right here, you're going to have lambdas all along the diagonal. There will be no lambdas anywhere else because lambdas come from this lambda I thing. So lambdas will only be on the diagonal. And as I find the determinant of this matrix here, however many rows and columns it has, it's going to give me a polynomial in lambda, okay? Now that polynomial in lambda will always have a positive leading coefficient when I put lambda first. If I do A minus lambda I, then the coefficient, if it's 5 minus lambda and negative 1 minus lambda, then my lambda is going to have a positive leading coefficient sometimes and a negative leading coefficient sometimes. And I just don't like messing with that. So this is the way I like to do it. Is there value to doing it the other way? Of course. But this is how I like to go. Okay. So that's that. Now, if I do a 3 by 3 matrix, let's find the characteristic equation and eigenvalues of B here. So I want to do the determinant of lambda I minus B. Now again, this is easy. You just take the main diagonal, and on the main diagonal, I'll just do lambda minus 1, lambda minus 2, lambda minus 5. Then everywhere else, just make it negative. Negative 2, negative 3, 0 and 0, negative 4, and negative 2. All right. So now let us find the eigenvalues by taking this determinant. What we'll do is we will do a cofactor expansion along the middle row. Okay, so that's nice. So that's plus, that's minus, that's plus. So it's going to be lambda minus 2 times the determinant of the submatrix, which is lambda minus 1, negative 3, negative 4, lambda minus 5. The zeros kill the other two, right? Which gives me lambda minus 2 times lambda minus 1, lambda minus 5, 4, sorry. Minus, 3 minuses, minus 12. Okay, now this is fairly typical right here. I have lambda minus 2. I need to expand this thing, so I get lambda squared minus 6 lambda plus 5 minus 12. So lambda minus 2. Lambda squared minus 6 lambda minus 7. And we're almost done. Lambda minus 2. Lambda minus 7. Lambda plus 1. And I want to know when that's equal to 0. And those lambdas are 2, 7, negative 1. Now, this was fairly easy to factor this time because I had a row of zeros, right? Because I had a row of zeros, it essentially factored out one of the things already. Had I gone along the first row, it would not have been as nice, and it would have required me to do some expanding and some factoring, and it would have been kind of yuckier. But as we can see, just like in a previous chapter, one of the harder things about the section was not actually the new stuff. One of the harder things was actually factoring polynomials, and so that comes up again. So make sure we're up to date on factoring polynomials. I have one more that is going to be easier. So watch this. When is it a lot of work and when is it not a lot of work to find eigenvalues? Now check out this one called D. If I do lambda I minus D, okay, what am I going to get? I'm going to get lambda minus 1, lambda minus 4, lambda minus 6 along the main diagonal. Zeros all below here, and then negative 2, negative 3, negative 5. Okay. Now, when I find the determinant of this matrix, I'm going to do a cofactor expansion along the first column, which gives me lambda minus 1. And the other two go away. And I end up with the determinant of this smaller submatrix. Okay, well, that one's just going to be lambda minus 4 times lambda minus 6, and then minus 0 because of that 0 down there. So what this thing did was it essentially killed all of the other terms. And so the determinant of a triangular matrix like this one is just the product of the main diagonal, which is what we have right here, lambda minus 1, lambda minus 4, lambda minus 6. And that's equal to 0 when lambda equals exactly the things that are on the main diagonal, okay? And so if you have a triangular matrix, then the eigenvalues are simply the entries on the main diagonal, and that's it, okay? So this isn't so bad, and if you want to say on my very first example, I kind of cheated by giving an easy one. You'll notice in a 2x2, it's triangular by just having 1 0 there in that spot. So yeah, I made an easy one for my first one, but that was on purpose, okay? So this is a theorem right here, which is if A is an n by n triangular matrix, upper or lower or diagonal, then the eigenvalues of A are the entries on the main diagonal of A, and that's it, okay? So next, here's a theorem that kind of summarizes some of the behavior of these eigenvalues. And that is, if A is an n by n matrix, then these are all equivalent. So all of these 4 things are equivalent. if you have an eigenvalue, then the system lambda I minus a has non-trivial solutions. That's what we just discovered, right? There is a non-zero vector x such that ax equals lambda x. Okay, well, this is the definition of being an eigenvalue, so that's good. It says there is eigenvectors, and lambda is a solution to determinant lambda I minus a equals 0. Well, that's what we just did also, okay? Now, an important follow-up thing to this is how and what happens with these eigenvectors with other eigenvectors in a particular eigenspace. So 171 says, suppose that A is a matrix and lambda is an eigenvalue, and U and V are eigenvectors corresponding to lambda. Show that every linear combination of U and V is also an eigenvector corresponding to lambda. Okay, so what I know is that let me change colors here. I know that AX, AU is equal to lambda U. And I know that AV is equal to lambda V. So then what is A times, let's call it C1U plus C2V? All right, well, that's going to be AC1U plus AC2U, not U, B, which is C1 times AU. I can do that in whatever order I want, plus C2 times AV. And from our assumptions here, we know what those are. That is C1 times lambda U plus C2 times lambda V. And I can factor that lambda out to get C1U plus C2V. Okay, well, there we go. I have A times that vector equals lambda times that vector. So if I have an eigenvector and an eigenvalue, then for every eigenvector that corresponds to lambda, then every linear combination of all of the eigenvectors that correspond to lambda is still an eigenvector that corresponds to lambda, okay? So this is really good. And so what we end up having is we end up having eigenspaces. And this goes back a little bit further to something we did in a previous chapter. If you have bx equals 0, and I know I've left off the little vector symbol there, that's okay. Then that is actually a subspace of Rn, okay? Because if you're a solution to bx equals 0, then you can add those and you're still a solution to bx equals 0 and multiply by constants, and there you go. So we don't just get eigenvectors, we actually get eigenspaces, okay? So a little better than not just a single thing, actually a lot of different things, okay? So next, we already found the eigenvalues for this thing. How do we find the corresponding eigenvectors? Okay, how do we do this? All right. Now, what we do is this thing, we already discovered, it has eigenvalues of 5 and -1, okay? Those are the eigenvalues. So what we need to do is we have to plug those back into lambda I minus a, and we need to find the vectors that satisfy this linear equation. And the good news is we already have lambda I minus a somewhere. Like when we start from scratch, it'll be on the same page. We'll already have this thing. And what we do is we just plug them all in. And this just looks like lambda I minus a, and then the 0 vector over here, and row reduce that thing, okay? So let's see what that looks like. So for lambda equals 5, well, what happens? Okay, let me write down lambda I minus a over here so I can refer to it. So for us, that's lambda minus 5, -2, 0, lambda plus 1. And so we'll plug in 5 to that. So plugging in 5 gives me 0, -2, and then 0, 6. These will always be very easy to row reduce, although I suppose there's no shame in getting a calculator out for doing this, but you can do them in your head, okay? This will row reduce to this matrix, all right? So you can row reduce these in your head. There you go. Now, we talked in the previous section about how to do this. What do I need to do? Well, who is the free variable and who is not? Well, x2 equals 0, right? Like that's what that first equation says. X1 has nothing, right? So x1 is a free variable. And so that means that the eigenvector, okay, in this case, is x equals t0, okay? Now, I just need to find a single one. There's a couple ways to think about this. I could just factor out the t, and when I do, I'm left with a vector, and this vector right here actually is the basis vector. Or you can just pick your favorite t. So pick t equals 1, and there you go, you have an eigenvector. Like I said, any linear combination of eigenvectors is still an eigenvector for this thing. So pick whatever t you want. You want to pick 2? Great. You want to pick 3? Great. If you pick 3, then you actually get that very first problem that I did on the first page, okay? So I picked a different 3 just so it wouldn't look like 1, 0. And so for lambda equals 5, I have 1, 0 as the corresponding eigenvector, okay? And then it is understood that 1, 0 is actually a basis for that one-dimensional eigenspace, all right? Then we do it all again. What about lambda equals, what was it? I already forgot. -1. What about lambda equals -1? Well, let's plug that back in to our lambda I minus a. And so -1 minus 5 is -6, -2, 0, 0. Okay. So then this row reduces also. Like I said, they all row reduce very easily. This one is, all I have to do is essentially divide by -6, and I get 1 and 1/3. I can divide by -6. And so there we go. X2 this time is free, and x1 is equal to -1/3 t, right? So the very first equation says, right here, says x1 plus 1/3 x2 equals 0. So subtract that over, I get x1 equals -1/3 x2, and x2 is, oh, by the way, t. All right, so that means that our eigenvector is going to be -1/3 t and t. Okay, now pick your favorite t. A good t to pick, I should say, pick your favorite t. Pick your favorite non-zero t, because that's just going to kill it. How about 3 or -3? So I'm going to pick t as 3, which gives me the eigenvector of -1, 3. Okay, and again, there's not just one. There are lots of different values of t to pick. And so I found the 2 eigenvectors that correspond to the 2 eigenvalues. Okay. Now there's a couple questions that you might be thinking at this point, and we will come back to some of those. All right. Next one. How about a 3 by 3? Now this 3 by 3, we already found all of the eigenvalues of this one in a previous problem. Okay, so it had 3 of them. They were 2, 7, and -1. That was from example 169. Let's just do it for one of them, okay, because I want to keep this video kind of short, but I do want to show you the 3 by 3 case. So lambda equals 2. So what is lambda I minus a? And that is lambda minus 1, -2, -3, 0, 0. Sorry, 0, -4, -2, 0. Lambda minus 2, lambda minus 5. I don't think I did that in the best order. Anyway, So lambda minus the stuff on the diagonal make everything else negative. Okay, so now we take lambda equals 2 and we plug it in. So I get 1, -2, -3, 0, 0, 0, -4, -2, and lambda minus 5, 2 minus 5 is -3. Okay. Then we row reduce. The 2 by 2s will row reduce easily. The 3 by 3s won't row reduce as nicely. Okay. So this row reduces to 1, 0, 0, 0, 1, 3 halves, 0, 0, 0. Which means what? Well, it means that x1 is equal to 0. x2 depends on x3, and x3 is free. And so what is it? -3 halves t. Okay. So that means that my eigenvector is going to be 0, -3 halves t. That 0 looks like a 6, sorry. And t, pick your favorite t. I like 2. And if I pick 2, I get 0, I'm sorry. T is 2. And in that case, x equals 0, -3, and 2. And so I just found the corresponding eigenvector to the eigenvalue 2. And in the 3 by 3 case, I would just do that over again, okay, for the other two. And you can see how these kind of start to mount up. All right, so let's talk about something cool that we can do with these, all right? Now, what if I wanted to do this example right here? Okay, so what about this thing, 1, 2, 3, 0, 2, 0, 4, 2, 5 to the 5th times 0, -3, 2. Just kind of look at this and just kind of appreciate if you were having to do that by hand, what it would look like. Well, this matrix times this matrix would give me 9 dot products to do, right? Just for the matrix squared. And then with another 3, with another 9, another, like this would take me a ton of work to do, like even as a calculator, like a bunch of calculations to do. Now, it's not that many. The calculator could do it pretty quickly, but a lot of calculations. And even if you multiplied a times this and then another one times that, you could cut down the number of calculations you had to do. But let's go back up here. If I wanted to do a squared x, that requires n squared dot products, then it's a lot. But if this thing is an eigenvector, then a squared x is a times ax, and we know that ax is lambda x, right? Then you can take that lambda out, and then that's lambda times ax, which, oh, by the way, is another lambda x. And so a squared x is just lambda squared x. And so this is a matrix that I know the eigenvalues of. And oh, by the way, this is an eigenvector. It's actually the eigenvector I just computed. So this is just 2 to the 5th times 0, -3, 2. Which is just 0, -96, 64. So we can see that if we know things are eigenvectors, then a lot of calculations become much easier, okay? So this would have been, this thing right here would have been a ton of calculations to do by hand, but because I know things about eigenvectors and eigenvalues, this became a very, very short problem, okay? So there's an application. Now, what I want to do now is just show us start to finish what all of this looks like, okay, for the 2 by 2. And I have 3 examples. I'm going to do one of them. I'm going to do the easy one, of course. And then I will let you do the 3 by 3 and the 4 by 4 case. The 4 by 4 is easier than it looks, so just give it a try. But I will do A, and then I'm going to have you try B, and I can post the answers to it online. And then I'll have you try C, and I'll post the answers to it online. So notice that C there is triangular. So this is not nearly as bad as it looks. Okay, but I want you to try that before I do it. So let me go back and I'm going to do the 2 by 2 case, and let's just see what finding eigenvectors and eigenvalues looks like from start to finish. Okay, so I'm going to write a little bit small because I don't have a ton of space here, but I need the determinant of lambda I minus a, which is the determinant of lambda plus 2, negative 4, negative 1, lambda minus 1. And I want to know where that is equal to 0. And so I get lambda plus 2, lambda minus 1, minus 4. So I get lambda squared plus lambda minus 2 minus 4, lambda squared plus lambda minus 6. So I have 0 equals lambda plus 3, lambda minus 2. So my two lambdas are lambda equals negative 3 and positive 2. Those are my two lambdas. Okay. Separate that from the rest. Keep in mind, I'm going to need this matrix right now. So put that in an accessible spot. So let's do eigenvectors for each of these. So lambda equals, let's start with negative 3 because I wrote it first. We'll start with negative 3. So I'm going to row reduce lambda I minus a on the left and 0, 0 on the right. So when I plug in lambda equals negative 3 to this, I'm going to write that matrix here. So negative 3 plus 2 is negative 1, negative 4. Then I get negative 1, and negative 3 minus 1 is negative 4. Okay, like I said, these are going to row reduce very easily. That bottom row just goes away, and multiply the top one by negative 1, and I get 1, 4, 0, 0, 0. Which means that x1 and x2 is free, and x1 is negative 4t. Pick your favorite t. How about t is 1? And I get the eigenvector is negative 4, 1. So I just did it. I got the eigenvalue and the corresponding eigenvector. Let's do it again for lambda equals 2. Plug it back in again. Okay, so the yellow matrix up there. So I have 2 plus 2 is 4, negative 4. Negative 1 and 2 minus 1 is 1. Row reduce that. You can see that the one of the columns is a multiple of the first one. So this is just going to row reduce to 1, negative 1, 0, 0. Again, if you want or need to use your calculator, there's no shame in that. We haven't done a ton of these, but that's how it row reduces. So then I can see that x1, x2. So x2 is free again, and x1 is actually equal to x2. So that's very convenient. Pick our favorite t, and our favorite t is, unless it's fractions, it's usually 1. So then the corresponding eigenvector this time is going to be 1, 1. And there we have it. I have another eigenvector and a corresponding, another eigenvalue and a corresponding eigenvector. So this 2 by 2 matrix had 2 eigenvalues, and each eigenvalue had 2 corresponding eigenvectors. And this is what one of the problems looks like from start to finish for a 2 by 2 matrix. And we're going to have to do this a lot in chapter 7. So hopefully this problem was very good. And I have to do a few of these that you kind of settle into routine. On B here, B is going to be a bit more work, and I want you to try it, and I'll post the solutions online. And the same thing goes with C. So those are my 3 examples here. we're more or less done with how to compute eigenvalues and their corresponding eigenvectors. But there's one last thing I need to clean up, and this was the page that I added later on. There actually are a couple things that I want to mention here, a couple of words that what happens if you have a eigenvalue that is actually a repeated root of the characteristic polynomial, okay? So let me just go over what this is briefly, and then what we do with this will happen in another chapter, okay? But I wanted to just kind of put a nice bow on this and tie it back in. So here are two matrices that are both diagonal, okay? 3, 0, 0, 3, and 3, 2, 0, 3. In each case, when I do lambda I minus a, I have lambda minus 3, lambda minus 3, lambda minus 3, lambda minus 3, and negative 2. And then the determinant are both lambda minus 3 squared, okay? So both of these things have the same characteristic equation, although they are different, okay? So here are some words I'm going to define, okay? And I have seen some books define a few of these words differently, okay? So work with me on this. I'm going to call the algebraic multiplicity of this to be the multiplicity of lambda as a root of the characteristic equation. So in this case, I'm going to say that the algebraic multiplicity of 3 is 2 for both of these matrices, okay? So lambda is a root of multiplicity 2 of the characteristic equation, so I'm going to call that the algebraic multiplicity. Then an eigenvalue is called repeated or degenerate if the eigenvalue has algebraic multiplicity more than 1. Okay, so repeated is when they will have a multiplicity that's more than 1. Okay, then we're going to call the geometric multiplicity is the number of eigenvectors that correspond to lambda. All right, the number of eigenvectors that correspond to lambda. On the previous problems that we did, we had a bunch of different eigenvalues, and each of them had one single eigenvector that went with it. So those had geometric multiplicity 1 and algebraic multiplicity 1, okay? Now, it turns out when they're repeated, some things can happen, okay? Now, if the eigenvalue is called complete, if the algebraic multiplicity is equal to the geometric multiplicity, okay? So that's going to happen for A up here, where when I find the corresponding eigenvectors, I'm going to have 2. So this has a algebraic multiplicity of 2 and a geometric multiplicity of 2 because there are going to be 2 of them. Now, in the defective case, what happens is that I have an algebraic multiplicity of 2, but then there's going to be a geometric multiplicity less than 2. So I'm only going to have, in this case, one eigenvector for my double root, right? And that's going to be bad. So let's just see what this looks like for both of these cases. This shouldn't take too long. So for the case A, right, 3, 0, 0, 3, lambda I minus a is just lambda minus 3, lambda minus 3. So when I plug in lambda equals 3 to this thing, I get 0, 0, 0, 0, 0, 0. And what happens is x1 is free and x2 is free, but they're free from each other also. So the eigenvector looks like st, which is s times 1, 0 plus t times 0, 1. And so what I get here is 2 eigenvectors. Okay, so I got 2 eigenvectors that went along with that one eigenvalue, right? And that was the situation. In case B, when I get 3, 2, 0, 3, lambda I minus a in this case just has a 2 in it. And you can see what happens. When I plug in 3, I get 0, 0, 2, 0, which does not give me two different eigenvectors. Only one of them is free. This row reduces very stupidly. I don't even know why I'm writing this down. So this tells me that x2 is 0 and x1 is free. And so we did this in a previous example. This gives me the eigenvector of 1, 0. Okay, pick your favorite t. My favorite t is 1. And so you can see that in this case, I only get one eigenvector. And so that's what I mean in all these definitions here. Okay, so in both cases, A and B, lambda equals 3 was a root of multiplicity 2 of the characteristic equation. So in each case, it has a algebraic multiplicity of 2. But in case A, it has a geometric multiplicity of 2, and in case B, it has a geometric multiplicity of 1. Okay. So that's going to give this a problem for us when it comes to the next section. Okay. And that's it for chapter 6. Give those couple a try, and I will post the solutions on Canvas. Okay. Have a great rest of your day.